recent. Okay. So we put the book up here. So just to let you know where we currently are. Yeah, we did quadratic functions last time. So we talked about parabolas. And let's do a quick couple of practice problems just to get back into this. You guys all see the red pen? Sometimes I have people that can't see it too well. Is everybody cool with that? I have other pens. What is this the function for? What kind of a shape if I graphed it?
A parabola.
Parabola, that's right, parabola. Don't say parabola, that's a bad idea. Can anyone tell me anything about the parabola based on just this function form? Vertex. What's the vertex? HK. Can anyone tell me, in terms of something we discussed earlier this semester, why it makes sense the vertex is HK? Just from the function. Yes, transformations, kick ass. One word answer, I love it. Right? So this would move everything a left or right h, depending on what side it is, and up or down k. So of course the vertex starts at 0, 0, so it moves exactly h, k. So of course the vertex is hk. Okay, I like it. Why does it kind of suck to put something into this form? So if I had something like, let's see, what do you got, Jeff? If I had to put this into that form, why does that kind of suck? Does anyone remember what method that requires me to apply? Completing the square. I love it. And remember there's a handout I believe I put up on the, or I can't remember, one of the two. What really sucks about this one, notice how this has to be a 1, right? Right here it's got to be a 1. So what do I need to do first? Is that a 1? No. So what do I have to do? Take a 2 out. And leave some room, right? Now it's funny, it's just to let you know, last night I had my Calculus 2 class, and I was reminding them how to complete the square, because it's important to know. It comes up in a lot of different places. Okay. So again, doesn't it already start to look more like this? What's A? I already know what A is. 2. This is eventually going to look like this, right? And then whatever number ends up out here, it's 7 at the moment, but there's going to be more stuff happening in a second. That's going to be my K piece, my Y piece of the vertex. So it's already looking more like what it's supposed to. Do you guys remember the steps on completing the square? Say again? Sorry? Yeah, half the middle dude. So -3, and then you take that number and you square it. You're almost dead. Say again? No, be careful. There's not 2 sides here. All on one side, right?
Right.
So if I add something, I have to at the same time subtract it. I really want that to make nothing but sense.
Right.
So if I put a +9 here, by the way, real quick, does the function have a 6 here? No. Right? Isn't that 12?
Mm-hmm.
You with me? And this is not 1x squared, it's 2x squared. I just put the 2 there. So I just put a +9, but what did I actually just do? What did I add 9? What's this? 18. I just added 18. Do you guys see that? So I better at the same time subtract 18. So again, it's kind of silly. If I have 7 and somebody adds 18 to it, how do I make it 7 again? I subtract 18, right? That's all that we're doing right there. If I add 18 and I do nothing, I change the problem. I have a different parabola. It's not the same as it was at the beginning. Everybody see where that 18, that minus 18, why is that there? Does everybody see why that's there? If not, it's okay.
Are you subtracting 18 because?
So yeah, are you cool? Everybody's cool with the 9 here, right? This is the completing the square step, so I know I've got to add 9 right there. But just like that's not really a 6, it's 12. This is not really a 9, it's 18. If I multiply this through, that's plus 18. If I subtract 18, it's the same parabola. I haven't changed it at all. I just reorganized it. Right? Because we're crazy. We just want to reorganize it. Notice this, the completed square seems horrible, but it's awesome. You just cut the middle dude in half and then square. This number is what goes here. This number is how it factors. So you don't even have to factor it. It's already factored for you. And then what do you have out here? Minus 11. So what's the vertex? Yeah, vertex is 3, right? It goes right 3, down 11, right? Vertex 3, negative 11. Is that cool? And then what's the, can somebody see the y-intercept real quick without doing any work? Barely any work. How do you find the y-intercept always? Make x 0, correct? So isn't this form better for that? If I make x 0, what's the y-intercept? 7, 0, 7, right? Okay. You guys doing okay? Okay. All right. Yes?
What we get when it isn't like divisible?
Say again?
Like what we get.
Okay, real quick. I'll do, real quick. Let me do one more thing with this. What was that I was about to do? Scheisse. Forgot, damn it. All right, let's do one where this is not nice, right? Just real quick. What was I going to do? Oh, well, too bad. Okay. So everybody got this here? Okay. What was I going to do? I just can't remember. Okay. Go get old kids. All right. Real quick. What if I had, I'm just going to do completing the square kind of stuff on. Here, let me make it really disgusting. There we go. That's going to be. I really want you to see. Can you guys see how this is going to be really disgusting? Because what do I have to do first? Move the 5 over. What's the major problem? What's the major immediate problem?
3.
The 3. Completing the square is based off that first coefficient being 1. Right? So if I take a 3 out, what goes here? Yeah, I'm dividing the 3 out, so this will be 11 over 3. Are you guys excited about that?
No.
Okay, it's appropriate. Now, somebody else, tell me the first step. I don't care what the number is. What's the first step in completing the square?
Half of the 11.
Yeah. So take the middle term and take half of it. So this is what I do when I have a fraction. I don't divide it by 2. I cut it in half, which is the same thing, correct? So what is half of negative 11 thirds?
Negative 11 over 6.
Negative 11, 6, okay, cool. And then somebody else, what's the second step now that I have that? Square. Now real quick, is that a pretty number? Would we consider that to be a number you want to show up? No. Was it difficult to get to? No. What about this? Is this difficult? Negative squared is positive. What's 11 squared? 121. What's 6 squared? Holy shit, right? Okay. Again, is that a number you wanted to show up? No. Was it hard to get? No. Now what, Jeff? Okay. Now it gets nice. Now it gets really cool. So I have 3. Well, I'm sorry. Let me do this. I left room for me to do this up here. What goes here? Yeah, plus 121 over 36, right? Now, real quick, do a little side work. What did I actually just add? 3 times this, correct? So I can do a little side work. What's 3 times 121 over 36? Stay with me. I know the numbers are gross. They're not what you wanted. It's not difficult, though.
363.
Well, what can I do here? So it's 121 over 12. So what did I just do? Didn't I just add 121 over 12? Right? Just like last time it was 2 times 9 is 18. I actually had added 18. So I actually, by putting this here, how is this different from the original problem? It's got a plus 121 over 12. Yes? So I better do what at the same time? Subtract 121 over 12. Again, this is where a lot of you guys would just sort of go, no, and then go to the next problem. Well, there's not a lot to do with these fractions. There isn't. I haven't actually done too much with fractions except for this. Everything else just sort of came out. All right. Stay with me. So now, watch this. Do you want to factor this?
No.
It's already, but here, we don't have to. It's already factored for me. So what's that gonna, it's gonna look like this. X minus 11 over 6. I really want you to understand. The first step of the completing square tells me what it will look like when it's factored. The second step tells me what I have to add here to make it go there. I don't have to factor shit, because it's already right there. Now, here's the most work I have to do. How do I do 5 minus this?
5 times 12.
Yeah, you need LCD. Times 12, times 12. 5 times 12 is 60. Minus 121 is negative 61 over 12. Again, does that look nice? No. Was it harder than the other one? Minimally. There were a couple of fraction things I had to do, but not like a really intensive one. And to complete a square is just so brute force. There's not that much like thought that I have to involve in it. Cut this guy in half, no matter what the shit it is, you can cut it in half. And then square it. Okay, I can do that. So what's the vertex? 11 over 6. And there's 61 over 12. Do you want that to be one that I ask you to graph?
No.
No, and that's normally I would not ask you to graph. I could give you a problem like this and say find the vertex. I would not ask you to graph this by hand because that's not terribly easy to do.
You get extra credit for you?
Maybe. I do extra credit, you know that. So we'll see. If I remember, I might make that up. What's the y-intercept?
5.
0, 5. 11. And then from these two things, you could graph it, but this one is not one I would make you graph. Well, now I remember what I wanted to do with that other one. Damn. Okay. This is a horrible. All right. Do you remember? Okay, real quick. That last problem we did, the nicer one. What was it again? It came out to be. It was 2x squared. Somebody have it? Minus 12x plus 7. Okay, thank you. And the vertex we got was. Remind me. Sorry. 3 negative 11. Okay, now real quick. Just to review, you guys remember the shortcut to get the vertex? Vertex shortcut. I'll get it started. Let's see. I'm pretty sure we talked about this. Negative b over 2a. And it comes right from quadratic formula. Negative b plus or minus shit divided by 2a. So the negative b over 2a is in between the two intercepts, which is exactly where the vertex is supposed to be, yes? It's got to be right in the middle. So what's b here? So it's negative, negative 12. And what's a? 2. So we have 12 over 4 is 3. Right? And then I plug 3 back in. Twice 9 is 18, minus 36 is negative 18, plus 7 is negative 11. Okay, all right.
Wait, do that again?
So once you do the shortcut, it just gives you the x piece of the vertex, right? So shortcut for the x piece. How do we get the y piece? Just plug x in. And blah, blah, blah. So we did a few examples last time. I even gave us kind of a gross profit one, and you just plug stuff in. You just plug stuff into here. Okay, maybe. All right. So that's a review of what we did last time. So today, we're going to expand what we're looking at. We're going to start looking at powers other than 2. Somebody's phone is happy about that. So these are called power functions because math people sometimes are not very creative. They're functions with powers in them.
Those called power functions.
So a power function looks like this, where P is a whole number. Let me make sure this book defines it the same way I did. Actually, I think they do, yeah, they do, okay, good. I think they make it the more general. That would be awesome. Okay, there. Yeah, good, okay. Not a home, a real one. Good, beautiful. Okay, I was a little worried it was starting us off slow. So, it needs to be able to be written in this form. So, what about this? Is that a power function? Why? How else can you write the square root of x? X to the 1/2. Right? Is that cool? Because the square root cuts things in half multiplicatively, and the exponents are based on multiplication. So if I put a 1/2 in the exponent, that means half multiplicatively. Yes? So it's if it can be put in this form, it is a power function. What about this here? Can you take all that and put it into this form? And you're like, dude, I don't know. No, you can't. There's no way. There's all pluses and minuses, and there's division. That's not going to work. But what about this? So this is a no. This is a yes. What about this here? Yeah, I like it. Do you guys see how you can simplify that? Anybody? What can you do to the top? Take out a what? X squared. What are you left with? X plus 1. So what happens? Now, real quick, what x value are you still not allowed to use? This is a domain question. What x value am I not allowed to use from the beginning? -1. So it's a power function, but it doesn't work at -1. Same way that this is a power function, but where does it not work? Any x that is negative, right? Okay, maybe. So that's a pretty basic idea. If I can put it in this form, It's a power function. Okay. And by the way, it can have a coefficient. I think the book uses a k for some reason. Right? It could have like a, this is still a power function, 5x to the 11th. Right, so it can have a coefficient, and of course, these all have a coefficient of 1, so the coefficient could be some other constant, and that's fine. Okay, maybe. Okay, so that's a very basic idea. Not much to it. What's more interesting are a couple of things. There's a couple of things that are a little more interesting about power functions. X squared is really, really, really basic. What does it look like? You look at that parabola job, we all know, okay. So that's a little parabola, dude. Do you see how it's going up on each end? Right? As I let x get really, really big, positive or negative, it's going up. Yes? What about x cubed? What does that look like? Yeah, cool. I like it. All right. Looks like this. X cubed looks like a parabola where this guy fell out, right? So you go, oh shit. So what is it do? What is it doing at the ends? So let's do something real quick. I want to show you. This one is just this. What do you think this one here might look like? Is it going to look like this? Is that going to look like this? What do you think? Is it going to be that nice and simple? I love you guys. Do you think that this is going to be as simple of a graph as this one? Hell no. It's got a lot more stuff going on. So real quick, let's see. Real quick. Let's go to the best freaking website for math students, especially in pre-calc. Pretty sure I showed you this before. What did I do? Desmos. What did I do? Yeah. Yeah, just go to Desmos. So if I put in here y equals, you can even put in there f of x, why not? Where do we go? X cubed plus 4x squared minus 7x plus 2. All right, tell me a few things about this. What is it doing at the ends still? Say again? What's it doing on the lower part? What's it doing? Yeah, it's still coming up, right? On this side, it's like going down, just like the normal cubic. It goes down here. And of course, what's it doing on the other side? When x gets really big, positive, it's going up, right? So it still has this behavior at the ends. So again, we're very creative. We call that end behavior. What's it going to look like at the ends? But notice how I left the middle empty here. Because the minute I put more terms in, that can make the middle wobble, right? So that's exactly what we see here. How many turning points are there? 2. Yes? All right, let me do one thing to make this a little easier to look at. See if I can do this. Boom. Yeah. Shit, what did I do? Okay. All right, so now I can zoom in a little bit. Okay. All right, so maybe it's a little easier. Right, it's got 2 turning points, yes? And just a word that you should know by now. What's the degree of that function? 3. So degree means the highest degree term. So the degree of a polynomial, which is what this is the degree of the highest degree term. And the highest degree term is x cubed. So it's a 3rd degree polynomial, right? And how many turning points does it have? 2. Parabola, how many turning points is a parabola? That's degree 2. How many turning points does it have? 1. Interesting. All right. How many X-intercepts does this guy have? Just barely. 3. And that, I'm almost certain that I talked to you guys. Remember, have I uttered the phrase fundamental theorem of algebra? I think it was in that video we watched. So what the fundamental theorem of algebra says, the number of X-intercepts is equal to the degree of the polynomial. So this is third degree, right? This polynomial is third degree. It has 3 X-intercepts. Now watch this. Stay with me. Can somebody tell me, if I make 2 become 12, what should happen to the graph? If I make that 2 become 12, what should happen? You can do it. Say again?
It rises up by 10.
It rises up. Well, actually by 3, because multiply by 0.3. Let's see what happens. It should be roughly rising by 3. There we go. How many X-intercepts does that have? That's a really evil question I just asked. That has 3. And you're all like, Jeff, as you continue to state, you're old. Maybe you can't see that. That obviously has 1. It has 1 real intercept, correct? It has 2 complex. Do you remember when the video we watched and the dude picked it up and it was all colorful? And you guys remember that? I don't know if everybody was here for that. I showed a little video. Yeah. This does not have a real intercepts here because it doesn't hit the real axis, but it has complex answers. And we'll actually see that in a minute. I think I want to do an example with you. Maybe like right now, we'll do an example. I want to show you it happened algebraically, so you actually believe me, because you're all like, Jeff, that has 1. In fact, let's do that right now while I'm thinking about it. Let me show you the real and complex stuff happening. And this will be a nice review of something else that's coming up. So according to what I just said, how many answers should this have? 3, correct? It has, not only should it, it does. It just does. It has 3 answers. So I put an 11 there. It has 11 answers, right? That's a little crazy. Now be careful. That only works with whole numbers. If I put a 1/2, it doesn't have half an answer. So it only works with polynomial kind of equations. Okay. How do I, now the wrong way to do this, here's the wrong way. Don't even write this. Add 8, take the cube root, and you get 2, and then you're looking at me like, yeah, Jeff, 1 answer. Stop teaching, get out of this profession, right? What's the right way to do this? I don't know if you guys even, does anyone realize, is anyone out there going, why this shit's that wrong, man? We solved it. But we lost 2 answers. How do you factor this? Little dude, big dude, right? Yes? That's XXX. That's 2, 2, 2. What goes in the little dude?
X minus 2.
Yep. What goes in the big dude? X squared. At the end?
4.
4. And then what's the sign of the middle dude going to be? Careful. Plus. It's got to be the opposite sign. Right? Because what's the middle dude's job? His job is to clean stuff up that I don't want. It's got to have the opposite sign. And then it's 2 times x. Yeah. Listen to me right now. What we're about to get into will require you to know how to factor everything. Everything we talked about. All the factoring methods we talked about. I have a little thing I'm going to give everybody because I don't know if everybody printed it out for yourselves. We're going to do some example problems. We have to know how to factor everything. Cubes, squares, trinomials, GCF, grouping. Yes? Okay. So if you're not really comfortable with factoring, you kind of want to carve some time out to focus on that. It's got to be right there for you. What can I do now? I have something times something is 0. So either this is 0. And then you're like, well, there's the answer. It's 2, Jeff. Okay, that's the real answer. Or this is 0, correct? Isn't that how I do it when I factor? I just set each piece equal to 0?
Yeah.
And then how do I solve this? Can you factor that?
Yeah.
No. You can never factor the big dude in a cubes unless you forgot a GCF. Right? You can never factor the big dude in a cubes unless you forgot a GCF.
So you get
Negative b plus or minus the square root of b squared minus 4ac all over twice a. And do you see what's going to happen in here? It's going to be negative. Shit. Negative 2 plus or minus square root of negative 4 minus 16, 12. So that's why it didn't show up on the graph, because they're complex. Is that a complex graph? No. When the dude picked it up and it became all colorful, that would be a complex graph. I don't want to graph that, Jeff. I don't want to get out my coloring pencils and try to have this 4-dimensional paper that I would need. No, that's a little weird. We can't do that shit. And real quick, what's the square root of a negative mean? 12 is 4 times 3. Square root of 4 is 2. There's an I for the negative, and there's a 3 left inside. So let me do that on the side real quick. Square root of negative 12. Square root of negative 4 times square root of 3, yes? Square root of 4 is 2. Square root of negative 1 is I. Square root of 3, I don't know. So you have to be able to simplify radicals. And then what's the last thing I can do? Can I just kill these 2's?
No.
Why is that illegal? Because both of these are being divided by 2. So I can kill all the 2's. Negative 1, give or take, I rad 3. Bam. So the degree was 3, and I got how many answers? 1, 2, 3. Okay. Okay. Okay, so continuing on. So we got, just to put it up here again, I wish I would have erased it. X squared has got 1 turning point. X cubed, the end behavior looks like this, and it could do weird shit in the middle, like we just saw there, right? It depends on how many extra terms there are, what they all do. Real quick, why does it make sense? Real quick, let's see if you guys are cool with this. What was the thing I used? It was that one. No, it wasn't. I can remember. What's up there? X cubed plus 4x squared minus 7x, is that? Plus 12, sure. When x gets really big, which term in there is growing the fastest? As I make x bigger and bigger. 1, 10, 100, 1,000. Which term is growing the fastest? Is that growing at all? What is that always? 12. This is growing linearly. This is growing like a side of a prop like this, right? This guy, 100 cubed versus 100 squared. Isn't 100 cubed crazy bigger? Bigger? Sure. Crazy bigger. Yes, are you guys kind of with me? So now listen, end behavior is all about when x gets really big. So when x gets really big, this guy dominates. I really want this to make sense. So when x gets really big positive or really big negative, it's going to end up, these are going to be like nothing. If I put 1 billion in here, 1 billion cubed, and I'm adding 4 times 1 billion squared, that's going to be like nothing compared to 1 billion cubed, right?
Right.
It's like giving Bill Gates a penny. Here you go, man. He's going to just let it hit his chest and keep on. Well, give him $10,000, he'll probably just hit his chest and keep on. Are you guys semi with me? So compared to what this guy is, All this other stuff is irrelevant. So when x gets really big, it has to start looking like the basic cube function. But when x is really small, these guys do shit. They mean something. Maybe? I really want this to make sense. So that's why in the middle, if I have extra terms, it could do all kinds of weird shit because these guys get to actually do something. But when x gets really big, they're like drowned out by this guy. Okay. So if I gave you this, at the very least, you know that over here it's got to be going up, and over here it's got to be going down. What we're going to do in this chapter is start to figure out, how can I figure out what's going on in the middle? By hand, not, graphing in a calculator or on a website. Okay. So, what about x to the fourth? What kind of end behavior do you think that's going to have? For a really big positive x, it's really big positive, right? What happens when I put a really big negative number in? Depends. What's a negative number raised to the fourth power always? Positive, yes. 4 negatives cancels. Everybody cancels, right? So that will also be like this. So let's make this the most general we can. All right, here we go. So in a problem, what we're working towards is I'm going to give you something like this. And the very first thing you're going to do is find the intercepts and tell me what the end behavior is, right? And then the rest of the problem is going to be, how do I figure out by hand what's going on in the middle? Because weird shit can happen in the middle, right? So what do we have here? End behavior. So I can be given, let me put a 1 there, sorry. I can be given a function of a polynomial function, nth degree. So pretty cool with this? So like if n is 7, it's the 7th degree, and then it's got lower degree terms after that. Are you guys with me? So it's an nth degree polynomial. So 1, if n is even, squared, 4th power, 6th power, so forth. And a is positive. End behavior is going to look like this. And again, why does that make sense? Because if it's an even power, positive numbers I put in become positive. Negative numbers I put in become positive. So of course it's going to go up in both directions. Right, and then one more example. Look here. If I make this a 4th power, well, this could get exciting. See what happens here. Ah, shit! It's not the way I want it to be. Damn it! Let me do this. If I make this a 4th power. Yeah. Okay. It's not doing what I want it to. All right, that's a little better. All right. Do you see how it's doing weird shit in the middle, but at the ends it's going up? Weird shit in the middle, at the ends it's going up. So if n is even and a is positive, it goes like that. What if n is even, but a is negative? Then it'll go down, just like a parabola is either opening up or opening down, right? So that makes complete sense, but now we're expanding it to be any even power. It's going to go up at the ends if a is positive. It's going to go down at the ends if a is negative, and it's going to do weird shit in the middle maybe, right? Okay. So what if n is odd and a is positive? Like a cubic, right? If n is odd and a is positive, what's it going to look like? Yes, cool. I was waiting for somebody to do this. Yeah. It's going to look like, yeah, exactly. Down over here, up over there. What if n is odd? Odd. If n is odd and a is negative. It just flips. Yeah, we know that from transformations. It's going to be up over here, down over there. So by itself, that's not enough information to graph it, but it's huge to help me start. It's sort of like doing the edges of a puzzle first. Anybody in here do puzzles ever in your whole life? I don't mean right now, it's all you do is puzzles. I get out of class and I just do puzzles. Don't you do the edges first most of the time? I know some crazy people that don't. Of course we do the edges. So end behavior is sort of like doing the edges first. And then I'm going to worry about what the hell's happening in the middle, because the middle can get freaky. But the ends are always really well defined, what they're doing. Okay, maybe. All right, so that's one piece. Not the end. That's just one piece of this kind of problem. There we go. Somebody knows what I'm talking about. Next piece is a really interesting idea. So watch this. Let me see how we do this. That's a really good way. All right, let's analyze something. See how somebody already factored that? Isn't that nice? So we don't have to factor it. Oh, that's nice. Now, can somebody tell me the intercepts? What are the X-intercepts? It's factored, so I can just see them. Yes? How do I find the X-intercepts? I make what? Make y 0. When is this equal to 0? Well, what makes this 0? What value of x makes this 0? 1. Negative 3. There, that's it. That's all it is. When it's factored, I can just read off the intercepts. So these X-intercepts are 1, 0, and negative 3, 0. Is that cool? Yeah, stay with me now. We're going to start to develop what we need to know to fill in the middle. Once I got the end behavior, I need to fill in the middle. Okay, so watch this. I know it goes through 1, 0, and negative 3, 0. Yes? So I can actually plot those. What's it doing at the ends? Here's a really interesting question. Can you guys see the end behavior? Why does this suck? This is kind of nice that they factored it, but at the same time, that means it's harder to see the degree. You do not have to multiply this out. But if you did, can you see what the highest power would be? Third power, you guys see that? X squared times x. That's the highest power you would get out of this. Do you guys see that? So this is a third degree. So what's the end behavior going to be? What's it doing over here? Up, because it's positive, right? And what's it doing over here? Down. So I know it's like this. So see how it could be doing this. I can't, and watch this. If I go through that one and through that one, is that going to look right? I'm supposed to go up. So do you see how I have to turn somewhere, don't I? Now watch this. I really want this to make all the sense. Let me see how this is. I know I'm down here already. You guys see that? I know it's coming up to this thing like this. How do I know that? Because of the end behavior. But watch this. What do you get when you put a negative 4 in? And something you gotta get used to. Let me go ahead and make this little dude here. What is it? 1 and negative 3. So it's 0 at 1 and negative 3, correct? When I put a negative 4 in, what's the sign of the answer? All I care about is the sign. This is squared, so that's always positive, yes? And when I put a negative 4 in here, what do I get? Negative. So I get positive times negative. It's negative down here. So if I have a polynomial, what's the only way you can get from this side of something to that side of something? Is if it goes through the x-axis, correct? So if I put a number in on this side, this is -3. If I put a number in below this and it's negative, it's going to always be negative over there. Because the only way it can become positive is if it goes through an X-intercept. So I just have to put one number below -3 just to tell exactly what it is doing down here. It is below the x-axis. What if I put in, somebody give me a number in between these? 0. I love it. What do you get when you put a 0 in? Positive times positive, right? Okay, so it's positive here. And then give me a number above 1. 2. Crazy. What do I get when I put a 2 in?
1.
I get positive times positive. I don't care what the number is. I just want to know what the sign is. So I know if it's above the x-axis or below it, right? So it's positive. Now, I really want you to understand this next idea. I really want you to be clear. When I plugged in -4 in, I got -5 squared is positive times -4 plus 3 is negative. And that's why I put negatives here, right? Not a one jet. Positive times negative is negative. When I plugged a 0 in, I got positive times positive. And that's why these are all positives. What does that mean visually? It means it's above the x-axis there. And then when I plugged a 2 in, I got positive times positive, so it's still above the x-axis. Okay, now where did it change signs? Around which number did it change signs? -3. That's right where it changed signs, right? That's right. That is where it goes through. It goes through the x-axis. From negative to positive, it goes through the x-axis. What did it do at the other root? Did it go through? It turns. And why does it make sense? Because what's a parabola do? What's a parabola look like? Doesn't a parabola turn? Yes? So there's a shortcut to this. I'm going to do another problem. I'm going to show you the shortcut. But right now, what can we do? We can do this. This is a really rough sketch. We're going to improve our sketches, but this is just a really rough sketch. So what do we know? It's got to start down here. It's got to go through -3. And then it's got to come back and touch 1. And then it turns and goes up. So I had to start here. I know it goes through -3. It's got to be 0 at 1 again, so it's got to turn and come back to 1 and touch it, and then it's got to turn and keep going up. Did it match the end behavior it needed to be? Yes. It's a huge thing to check at the end, right? Now, is this a really good sketch? What's wrong with this if I wanted it to be an official graph? What's wrong with this? A huge thing that's wrong. Y-intercept, right? And more than that, what about the scale on the y-axis, right? Okay, so we're going to get this to be more refined. I just want to introduce one idea at a time. So we got end behavior, and then we got this idea. So let me see. Let me do this. See if you guys are cool with this. So what if I have okay, so let's try this fresh. And I do have a handout, so of course I do. We'll get that in a minute. Can somebody just tell me what the end, what's the degree of this polynomial?
5.
So this is a what degree? First. This is a second, and this is a first. So the highest degree, if I multiply this out, wouldn't I get an x squared there? And I get an x there, and I get an x there. X times x squared times x is x to the 4th. What's the shortcut? 1 plus 2 plus 1 is 4, right? I really want you don't have to multiply it out, but if you did, can you see that that's the biggest power you would get is x to the fourth? Okay. So what should the end behavior be? Yeah, it should look like parabola at the ends. And it's positive. I should have made it negative, but too bad. All right. So it's going like that at the ends. It's just in the middle, I don't know what the hell's going on, right? Okay. What are the intercepts, the x-intercepts? -4. 0. Good. -4, 0, 3. And should write him his points back. That's fine. So then you can go now listen. Which one looks like a parabola? Which root, which one of these came from a piece that looks like a parabola, so it's going to turn there? 4. The -4, right? So it should turn here, and it should go through those. I know that already. If there's an even power on the piece where a 0 came from, where an x-intercept came from, it's going to turn at that. If there's an odd power, it's going to go through. And we saw exactly that happen over here, right? So it's sort of a shortcut. This is called multiplicity. Oh shit, it's called multiplicity. So this has, -4 has multiplicity 2. It has an even multiplicity. So it's going to be like a parabola and it's going to turn. If it's an odd multiplicity, it's going to be like a cube and go through. Does a cube turn? Nope. Keeps going. It goes right through. Right? I really want this to make sense because I have calc students who don't know this. And that's one thing you're supposed to get from pre-calc is to understand multiplicity so you can make quick, rough sketches easy. Right? So I have less work to do here. So watch this. I don't even have to do any of this shit. And we're still gonna let's do one thing that's a little bit better. What's the y-intercept? I didn't really make a great one for this, but well, no, that's true. The y-intercept is too easy. What's the y-intercept? How do you find the y-intercept? You make x0. So if you make x0, what's the y-intercept? There should be no thought. 0. 0 times who gives a shit, right? So that's a horrible y-intercept. It's too bad for us. All right, so we're going to fill more details in next. I just want to focus on what we needed from this. So what are my intercepts, my x-intercepts? They are
4, 0, 3.
Yeah, -4, 0, and that's why it's also y-intercept, and 3. So again, this is still not good enough for a finished graph, but we're just introducing one thing at a time here. End behavior, so where does it start? Is it coming in towards that first thing like that, or is it coming in like from above or from below? From above. So I already know it's doing this. What does it do at -4? Turns. So I'm going to do this. And then where's it got to be sure to go next? 0. And it's going to do what there? Go through. And where's it got to go next? 3, and it's going to go through. You guys with me? Or against me?
So like each point has a parabola?
Yeah, all right, I like it. The curvature of these is not parabolic, but they look parabolic. I agree. Yeah. And so, like this looks like a parabola. Why does that make sense? Because -4 came from a squared piece. Let that make sense. It looks like a parabola around -4 because -4 came from a piece that was squared or raised to an even power. Right? What's it do? The other ones, it goes through like a line here, and it goes through like a line there because they both came from lines. Odd powers go through.
So it behaves that way because the square root is means the second power is the strongest?
No. So if I did make this little chart, -4, 0, 3. Is it 0 at each of these? Yes. Right? 0 at each of those. So now I just have to know, is it above or below the x-axis in each one of these places, right? Because again, what's the only time the polynomial can go from negative to positive or positive to negative? It has to go through the x-axis, right? So the only places it can become positive or negative is around these intercepts. So if I put in a negative 5, I'll get, so negative 5, I really want you guys to understand. If I put in negative 5 in, isn't this negative? Negative 5 plus 4 is negative. Negative 5 minus 3 is negative. And this is squared though, right? So this is negative times positive times negative. Right? Negative times positive times negative. And what is that? Negative times negative is positive. Times positive is still positive, right? And that's why at negative 5, it's up here. If I put in a negative 1, if I put in negative 1 in, this is negative, this is always positive, because it's square, right? And this would be negative. Negative times positive is still positive. Do you see how it's... So I know it's not going to change signs around negative 4, because negative 4 comes from a squared piece. Right? This is always positive. So if I'm below negative 4 or above negative 4, it's not going to change. It's going to be the same sign on both sides. Okay. And if I plug a 1 in, that'll be positive times negative. Now I finally get a negative, see? It's down. And then if I plug a 4 in, positive, so it's positive, and sure enough, up. But if you know multiplicities, you don't even need that. Okay, so let's do this. Let me see. Make sure I've talked about every piece on here. Blah, 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 blah. All right, let's do this. Do A, B, and C on number 1 on this here handout. And then I'll kind of help us with part D. Is the one that came out okay? Roughly? Okay. My printer started losing ink or something. Sorry. Do A, B, and C on that first problem. On these problems, I'm being a little more evil because I haven't